This video is actually an assignment for one of my engineering classes. We're just supposed to take a short amount of time to teach something to people, so please enjoy. The question I'd like to address today is, what is a matrix? Different people will have different levels of understanding of this topic. So maybe you're in high school and you've used matrices in algebra to solve systems of equations, but otherwise you might not know, why that works or where it came from. If you're a college student studying STEM, you might have taken a class already called linear algebra, and there's matrices everywhere, right? If you turn any page in a textbook, you'll see theorems and exercises in how to use these matrices. And you may understand those rules, but you still might not understand, the abstract concept of why we need these things and why it matters. And that's completely understandable. That's where I was coming from coming out of that class. And it all kind of clicks to me when I started practically using matrices, especially in a class called Aerospace structures. Now in aerospace structures, you're trying to analyze, structures, right? You're trying to see how you can make a structure that doesn't break. And two of your most important tools in that are strain and stress. If you're not familiar with those terms, you can think of strain as measuring the change in shape of material and how it reacts to that. And you can think of stress as measuring how the material handles force put upon it. And these are important properties. If you think of an object and just think about putting a ton of force on it, then the strain and stress is going to increase and increase and increase, and it's going to hit that critical point, which is where it won't return to its original shape anymore. So let's take a look at this scenario. We know the strain values in the x and y coordinate system, but what if we wanted to know the strain values in that rotated coordinate system? To convert the strain values from that coordinate system to the rotated coordinate system, we would need something called a rotation matrix. And proving that the rotation matrix works in the first place is a whole discussion on its own with matrices, because it's one of those things that's easier to prove using matrices rather than just normal math. Here on the left, I proved the rotation matrix using trigonometry and algebra, and it's one of those proofs that works out symbolically but doesn't really make intuitive sense. Because right here, the proof kind of just depends on you just knowing a trigonometric identity and being able to apply it, and it just so happens that it cancels out the terms and leaves you with the proper equations. Contrast this with the proof on the right using matrices. Now, I know it may look like a lot, but if you've taken linear algebra, then you might be able to see that the only ingredients here are the concepts of vector projection and the dot product formula. And those are some of the first two things you learn in linear algebra. That's pretty basic stuff. You could argue that the one on the left isn't that bad, but keep in mind that we're still in 2 dimensions, and if you keep extending this to higher dimensions and bigger matrices, the math is going to get out of hand. Imagine having to prove that without linear algebra. Anyway, back to rotation matrices. So if we were to write out the equations to convert our strain values, it would be this giant equation right here. Contrast that with the elegance of the matrix equations, and look at how much space it saves. Also, notice how at first glance you can kind of tell what's going on with the matrix equations without being told that you're rotating strain values, and that's because they're just grouped nicely within each matrix. Contrasted with the written out equations where you just have this mess of sines and cosines and plus and minuses, and it's just not as coherent. Also, another argument in favor of the matrix equations is let's type them into Mathematica and see who wins. Yeah, that efficiency. We love to see it. So, back to the question and my personal journey in understanding matrices. So, what is a matrix and who decided what that means? Well, let me make an analogy. What is a number? Who decided what numbers are, and why does 2 plus 2 equal 4? Well, if 2 plus 2 equaled 5, then that doesn't really translate to the real world, and it's not useful for us. Who decided that, 4 to the power of pi has an answer? Well, we kind of extrapolated an answer because with any other result, we can't use math to describe the physical world. It's not useful. Who decided that in Euclidean space we describe distance with that Pythagorean equation thing? Well, we defined Euclidean space to work with that distance formula because with any other result, it doesn't work. It doesn't translate to the real world. So it's going to be hard for you to make yourself feel like you understand matrices because it is abstract. I think like all math, it's not real. No one said it was real, and it doesn't have to be real. It's simply a tool that we use to understand the physical world.